reason it feels hot outside is the particles are moving faster outside because the temperature is higher. When those particles hit your arm, they leave a little bit of energy because they bounce off of your arm. The higher the temperature, the faster they move, the more energy they're going to hit you with, right? So thermal energy is just the motion of particles, and that's being converted into electromagnetic radiation. The process by which that happens is quite complex. I don't want to go into it. For now, we'll just say that it's a physical phenomenon that takes place. And the one nice thing is, and why this is so relevant to what we're doing, why we're studying it and what we're studying is that the energy from stars is very well approximated by black body radiation. So this concept of black body radiation is extremely useful when studying stars.
Jagrat, may I ask a question? Is it really correct to say thermal radiation, or should one be saying electromagnetic radiation?
So it's thermal kinetic energy is what I mean. You could call it thermal radiation, and people use that so if someone says thermal radiation, you assume black body radiation. So black body radiation and thermal radiation are generally taken to be synonymous terms.
Okay.
But the phenomena that's underlying it is the conversion of thermal energy into electromagnetic radiation. So there's three laws that we're going to study related to this phenomena of black body radiation. The first is Planck's law. So what Planck's law is, so in this graph, the first thing I should point out is the axis down here is wavelength, okay? So you have more energetic particles at smaller wavelengths, right? So I should have mentioned that before. If the most energetic particles have the highest frequencies. Less energetic particles will have lower frequencies, okay? But because frequency and wavelength are inversely proportional, right? Wavelength equals the speed of light divided by the frequency. It goes the opposite way. So the most energetic phenomena have the smallest wavelengths and the highest frequencies, and the least energetic phenomena have the longest wavelength and the lowest frequency. So here in this plot, the highest energy is higher energies are on this side for a photon or light wave, and the lower energies are on this side. Okay. What Planck's law says is, if you have a black body, it's going to emit energy at all wavelengths, not just one wavelength, at all wavelengths. And the way that it emits energy at all wavelengths is given by this equation right here. Now you don't need to write this equation down or memorize it. This is not, it's beyond what you guys are going to need to know. But it's simply to state that this equation is shown visually in these plots, okay? And what you see, the thing that I should point out is, what does this equation what does it mean, right? So what this equation tells you is, if you give me a temperature of a black body, I can tell you the intensity of radiation at any frequency or wavelength, okay? So if I give you a temperature, the only other, there's no other unknowns other than the wavelength. And at, like let's say 1 micrometer, I can plug it all into this equation. The only thing I don't know is temperature. So the only thing that really characterizes a black body is temperature, okay?
Can you tell them what you mean by intensity? Can you tell them the units that we are measuring intensity?
Yeah, so intensity is generally measured as ergs per second per centimeter squared per wavelength. It's complicated. I don't want to give you the... Think of it as just you know what intensity means, you know, kind of intuitively. Mathematically, it's a very complicated thing, and I don't want to confuse you. But just think of it as the brightness, right? But it's a normalized brightness. So the intensity at 1 is the amount of radiation you're receiving, okay? I apologize, it's quite complicated mathematically, and the units get really cumbersome. The units come directly from this equation here, and you can see it's going to be like very complicated units. But the point is that a black body is going to emit at all wavelengths, right? And the black body itself, the only really three parameters are temperature. If you know the temperature, you can characterize everything about the black body, okay? And here are some plots, right, of different temperatures. So here's like an object, if it was 3,000 Kelvin, right, which is something like 1,500 degrees or so, okay, Fahrenheit, what you're used to. from that object. Now the way you read this plot is, okay, I have this object, I want to know at like 2 micrometers, right, how much radiation is coming out. Well, looking at this plot, it'll be this number here, which is less than 1, right? And you can see that the peak of it is at about 1.2 micrometers, okay? And just so I should have mentioned this earlier, the visible part of the spectrum is about 400 nanometers to 900 nanometers, which in this is 0.4 to 0.9 micrometers, okay? That's the light we see, it's in a very narrow range. And more importantly, the colors that we see are related to the wavelength. Red, for example, is the reason the color appears to us as red is because it's the wavelength of that wave is about 800 nanometers. Blue, on the other hand, appears to be blue because the wavelength of that wave is 400 nanometers. And then all the other colors of the rainbow fall in between there.
So it's more based on wavelength, and then the wavelength is proportional to the frequency, so they all equal speed of light.
Well, the wavelength is inversely proportional to the frequency, right? And really, wavelength or frequency are they're exactly the same way. They're just 2 ways of describing the
So it's the wavelength that makes the color, not the frequency.
No, the frequency and wavelength, they both are, they're just properties, right? Like if you remember the wave, right? You could say, I could just as easily have said it was the frequency. So blue light has higher frequency than red light.
Yeah.
Because they're identical ways of describing the same phenomenon, right? So if you have the temperature of a black body, you can basically know what it's going to look, what kind of radiation it's going to, what the radiation it's emitting is going to be. And these graphs here show you that, right? And so a few things I want to point out is, 1, if you increase the temperature of a black body, you increase the radiation at all wavelengths, okay? So compare the 3000 to the 4000 curve, right, in this plot, right, to the 5000 to the 6000. When you increase the temperature, you increase the radiation at all wavelengths, okay? Is that clear?
So each curve is completely above the other.
Yeah, so maybe I should stop and ask, do these plots make sense? Do you guys have any questions about that? Because when you start looking at data, you might be looking at plots like this. So it's worthwhile to ask, do you understand what this is representing?
So EXP is some weird function that we
It's just e to the, have you ever seen like the function like e to the,
Base
it's
of
called the
natural logarithm.
It's called the exponential.
Base of natural logarithm.
Yeah.
EXP, that's what it is.
Yeah.
Well, you can write it exp or you can write it as e.
Okay.
Yeah. So sometimes people write it exp because it's hard to write like.
Oh.
Right. It gets kind of crunched up, so you can just write it exp, and then just have the whole thing. So they're the same thing. Okay, sorry, I should have made that clear. Any other questions?
Luckily you don't need it, but anyway.
Yeah, you won't ever need this. I just wanted to show you what these curves mathematically were. That they're this somewhat complicated, but not really that complicated curve. The only reason it's not that complicated is because everything's pretty much a constant here, except for temperature. And
See, basically, Zahid is just saying, if you have a black body at 3000 Kelvin, at this wavelength, it will emit this intensity of radiation. At this wavelength, it will be emitting this intensity of radiation. It will be emitting, nevertheless, radiation all throughout the spectrum. If you have a black body that's 4000, at every wavelength, it is emitting a greater intensity of radiation than the colder object. Yeah, but the peak has shifted towards smaller wavelengths, which is the same as higher frequencies. Right? Here's an object, black body at 5000 Kelvin. It again is emitting radiation at all wavelengths. Right? At this wavelength, it's emitting this intensity of radiation. At this wavelength, it's emitting this intensity of radiation. But the peak has shifted again to higher frequency or lower wavelength, which are the same thing.
yeah, so you could say, for example, right, that the 5,000, roughly speaking, the 5,000 degree black body is emitting about half of the radiation of the 6,000 degree black body at this wavelength, right? Because this is at 8, this is at 4 roughly. So it gives you the relative intensity. The units here are arbitrary units right now, so don't worry about that. But it's just a measure of the amount of radiation, basically. So I think Raja pointed out the other important thing. The first thing is that if you increase the temperature, you increase the amount of radiation at all wavelengths. The second thing is if you increase the temperature, the peak